In these problems, I'd like to draw free body diagrams for both block A and B. My diagram for block B will go on the left here, and I'll just represent block B as a dot, and then I'll put my diagram for block A on the right. Now in this particular situation, it's showing a hand pushing on A, and A can in turn push on B. The blocks are moving with constant velocity, and we do want to assume that there's some friction involved in the situation. If that's the case, then we know that as block B moves to the left, friction would oppose the motion of the block. So I could start with a frictional force acting on B. In order for constant velocity to be achieved, though, it must be the case that there's a forward force as well on B. And this I can call F of A on B. It's a normal force caused by the contact of the surfaces. A's surface pushes on B's surface. When it comes to their relative magnitudes, they would be a 1-to-1 ratio where the size of FA on B has to balance out with the size of FF. This is because we have to have constant velocity, and in order for constant velocity to be achieved, must be that the forces are balanced. We have a force of A on B that shows an interaction between two objects A and B. And anytime there's a force between two objects, Newton's third law says that both objects feel that force. More specifically, here's Newton's third law written symbolically. F of A on B is going to be equal to the opposite of F of B on A. They'll have equal magnitudes, but they're going to be 180 degrees opposite in direction. So since I drew a force of A on B pointing to the left, I have to also now draw a force of B on A with the same magnitude pointing to the right. Okay. A is going to also feel some friction, and friction has the formula Fk equals mu k times Fn. So in the friction formula, this is the size of the kinetic friction. That's friction due to motion. Mu is going to be a coefficient of kinetic friction, and Fn is the normal force between the surface of the object and the surface that's causing the friction. And so what this formula shows is that friction will be proportional to a normal force, and we would know that the weight of A is twice as large as the weight of B here. So if we were to include those forces, the weights, we would see a downward force there for B, which is balanced out by an upward normal force. But A's downward force would have to be twice as big. Because that normal force for A is so much bigger than the normal force for B, the friction is going to be larger for A. It's going to be twice as large. So even though I have a size of 1 here for the friction on B, I need to have a friction size of 2 for block A. All right, so what does this indicate for the size of the push on A? How big does that push have to be? Well, it has to overcome the force of B on A and the friction on A. So that push must have a magnitude of being 3. So the force of the push has to equal the sum of the force of B on A and the FF on A. Alright, that's the diagram for the first one. And right now it's just a somewhat qualitative but somewhat quantitative analysis. I haven't calculated actual newtons for these forces, but I'm just showing sort of relative magnitudes of them. When it comes to number 2, we would really see the same kind of thing as above. There would be a friction force of size perhaps 1 acting on B. There must be a forward force pushing it forward. We're still at constant velocity, so it's the same kind of drawing. One thing that's different here, though, for A is the friction is not going to be as large. So we might have this. And now the person doesn't have to push as hard because they don't have to overcome as much friction as before. They could push with a size of 2 here. That looks good. If we were to show also the weight of the blocks and their normal forces that are on them from the ground, it would look like this. Okay. Our next set of blocks is accelerating to the left. Now, as we can see in the friction formula, it doesn't actually include an acceleration or a velocity. This coefficient of kinetic friction is just a constant that's based on the surfaces that are involved, like the type of materials that are involved. That's what matters when it comes to the coefficient of friction. So it doesn't really matter how fast the object is moving or if it's accelerating or not. So when it comes to the friction here, I'm just going to let it be the same as it was in the above case. I'll let it have a size of 1. But this time we need that forward force to overcome friction. We need unbalanced forces. So I'll give that a size of 2, just to show that it's bigger than the friction. Now we have acceleration for block B. When it comes to drawing block A, though, he's going to have the same friction that block B has. But when I go to draw the reaction force of B on A, it needs to have the same size as the force of A on B. That is Newton's third law. This has to be a size of 2. Okay, now I'm going to decide how large the forward push needs to be. So the thing is, it can't just balance with the sum of 1 plus 2 here. It has to be larger than that because we need block A to accelerate. If the push doesn't exceed the backward forces, then A won't accelerate. So I can't just put a 3 here. That's not enough to achieve acceleration. I'm going to put a 4. If I push with a 4 in the forward direction and we have 3 in the backward direction, then that forward force of push will win, so to speak. And our block A will accelerate with a net force of 1 unit, which is the same as the net force that the other block had. So his net is 2 minus 1, which is 1. And this block A's net is going to be 4 minus 2 minus 1, which is also 1. So they have the same net force on them, so they'll both accelerate the same way. In this last one here, we have a larger block B. We also have constant velocity. Because it's larger, we do expect the friction to be more than we would have had for the 50-gram block. And since we want to achieve constant velocity, let's let our F of A on B match with FF. We have to draw a force of B on A, which is called a Newton's third law pair with the red force of A on B there, because they're equal and opposite, and they describe the same type of interaction, a normal force between these surfaces. Let's give A some friction. Just 1 unit is sufficient. And now let's balance A's forces by letting the push have a size of 3.